An erupting volcano is an awesome sight. We see it as a violent example of energy within the Earth. But to the geologist, it represents but one small part of a much bigger story, the beginning of the rock cycle. He begins by asking one simple question: how do solid rocks get melted? Today, we still don't have all the answers, but there are several theories which may explain much of what we can observe. All rocks contain small amounts of radioactive minerals, which decay slowly, releasing heat. As we look at the land surface, we realize that most rocks are buried under thousands of meters of other rock. Because it is a good insulator, rock allows heat within the earth to escape very slowly. Why then doesn't all the rock beneath our feet melt? Because heat generation is slow, almost equal to heat loss, and because the pressures are tremendous. The most probable clue to the melting of rocks seems to lie beneath the edges of continents, where drifting crustal plates collide. We know that belts of active volcanoes line the edges of all the continents around the Pacific Ocean. In fact, there are so many that the belts have been called the Ring of Fire. In the last few years, geologists have come to realize that some of the belts mark boundaries, where one crustal plate plunges under the overriding edge of another. As the bottom plate slowly moves downward, the friction between the plates causes the temperature and pressure to increase until the rocks begin to melt. Molten rock can work its way toward the surface by melting overlying rocks or moving up along breaks or cracks in the crust. This lava flowed out onto the surface and is called an extrusive igneous rock. If the magma had solidified before it reached the surface, it would be called an intrusive igneous rock. Intrusive igneous rocks are named on the basis of their mineral composition and the size of the various mineral grains which make up the rock. Igneous intrusions often occur on a gigantic scale. In the side of this mountain in California, the lighter colored rock was once a mass of molten material which pushed up the darker rocks. Such a structure is called a batholith. A similar intrusion formed this batholith in the mountains of Alaska. Erosion has uncovered its upper surface, but its roots are still far below ground. Because of their size, batholiths can most easily be seen on maps or from the air. A smaller structure called a lacolith forms when magma moves between existing beds of rock, causing them to bulge. This dome-shaped hill in South Dakota was pushed up by such a lacolith. Nearby, erosion has uncovered the igneous core of another lacolith. On a smaller scale, flat sandwich-like layers called sills form when magma simply squeezes between flat-lying layers of rock. This sill in the San Juan Mountains of Colorado forms a high cliff where erosion has cut a steep-sided valley. Magma may move into cracks, forming long, thin structures called dikes. If you look closely at the wall of this canyon, you can see many dikes showing as light-colored lines in the darker surrounding rock. In most places, dikes are exposed as a band of rock because both the dike and the surrounding rock have eroded at the same rate. But in the Spanish peaks of Colorado, the dikes were harder than the surrounding rock and have been left standing alone. In New Mexico, a gigantic tower called Ship Rock is all that remains of magma that solidified in the throat of a volcano after an eruption. Erosion over millions of years has removed the sides of the volcano, leaving the core behind. Magma rising underground gives off gas and steam. Some comes from the magma itself, but much more comes from water moving in underground toward the magma and being converted into steam. Along with the steam comes hydrochloric and sulfuric acid, carbon dioxide, ammonia, and methane, to name but a few. Active geothermal areas like this one in Yellowstone National Park occur only where magma is so close to the surface that groundwater can come in contact with heated rocks. Such areas usually contain a variety of interesting features. Water boiling underground may convert the soil to mud that comes bubbling to the surface as mudpots. Or the water may rise to the surface as a hot spring. Some hot springs leave mineral deposits on the surface, forming colorful terraces. When conditions are right, water may collect in underground channels until the heat and pressure cause it to burst forth from the conduit as a towering column of water and steam called a geyser. As magma forces its way upward, weak spots may allow it to break through to the Earth's surface. Then we give it the general name lava. When it cools, we call it extrusive igneous rock. Explosive eruptions occur when the magma contains large amounts of gas, which may blow great clouds of ash and cinders into the air. Occasionally, large blobs of lava are thrown out that solidify in the air as they fall. They usually assume a rounded or spindle shape and are called volcanic bombs. The ash and gas mixture from a large explosive eruption may spread out over a wide area, burying everything surrounding the volcano. This ridge in Yellowstone Park contains an interesting record of ash eruptions. Petrified tree trunks still standing were buried over 600,000 years ago in the latest of a series of ash eruptions. Geologists have been able to count 27 separate forests buried one on top of another. After one forest was buried by ash, hundreds of years passed and a new forest grew, only to be destroyed when another eruption occurred. In another part of the park, a tremendous flow of hot ash and gas spread out from a volcano. Near the top of the flow, where there was little pressure, bubbles of gas expanded. When the rock cooled, they were frozen in place. But at the bottom of the flow, something quite different happened, and the mixture cooled as volcanic glass called obsidian. Not far away in Yellowstone, this cliff was formed by an ash flow consisting of ash, dust, and broken fragments suspended in a very hot gas. As the mass cooled, it formed a breccia. Breccias vary widely, but they tend to be composed of sharp, angular fragments suspended in a fine-grained mass of ash and dust. In a violent eruption, a steep-sided cinder cone forms around the volcano itself. Because of the loose particles and the steep slope, cinder cones erode away rapidly. Capulin Mountain in New Mexico and Sunset Crater in Arizona are cinder cones from relatively recent explosive eruptions. More resistant cones are formed when violent eruptions alternate with quiet outpourings of lava. The lava covers the cinder layers, holding them in place and preventing rapid erosion. Mount Lassen in California was formed by such an alternating series of eruptions and is called a composite cone. Usually, a volcano forms a cup-like depression at its top called a crater. Some very large eruptions blow out so much magma that a huge crater forms called a caldera. At Crater Lake in Oregon, such an eruption left Mount Mazama without support, and the top of the mountain fell into the empty magma chamber. The tremendous caldera filled with water, forming today's Crater Lake. Magma that is composed of basalt is very fluid and produces quieter eruptions. Rivers of lava may spread out over the land surface. Often a shield cone forms which, instead of being very steep, is almost flat or dome-shaped. Fluid lava, called Pahoehoe, solidifies with a smooth or ropey texture. Sometimes the top of the flow cools and crusts over, while underneath lava is conducted in channels to the edge of the flow. After the eruption, the channels are left behind as empty lava tunnels. If lava enters a body of water, such as the ocean, molten material is squeezed out of tubes underwater. Cooling very rapidly, it breaks off and forms pillow-like chunks of lava. Pillow lavas are common around the world, but since they occur underwater, few people have seen them form. lava forms when the surface breaks into many jagged blocks. More than 900 years have passed since the eruption that produced this lava flow, yet only a few hardy plants have begun to grow on its extremely rugged surface. The world of molten rocks is certainly a strange one. Every eruption is different in one way or another. Lavas oozing down the sides of mountains, violent eruptions throwing ash fragments, dust, and gas into the air, or magmas moving through crustal rocks to form dikes and sills. The variations are seemingly endless. Each provides new clues, new answers, and new puzzles for the geologist as he tries to understand and explain the origin of igneous rocks.